Let's take a look at raising a complex number to a complex number. So let's take a look at 2 minus 2i to the z power. Let's figure out when 2 minus 2i to the z could be on the unit circle, so it has modulus 1, or it could be a positive real number or a pure imaginary number. To get started with this, let's do the following observation. So 2 minus 2i to the z. By definition, this is equal to e to the z times the logarithm of 2 minus 2i. Now, what is the logarithm of 2 minus 2i? Let's do that down here in the bottom left. So 2 minus 2i is going to be down here, over 2, down 2. And so the distance from the origin is 2 square root of 2. And the angle in question is negative pi over 4. So that means that 2 minus 2i is equal to 2 square root of 2 times e to the negative I pi over 4. And it's important that I chose an angle that is between negative pi and plus pi. And so therefore, by definition, the logarithm of 2 minus 2i is equal to the natural log of 2 square root of 2 minus I times pi over 4. So that's the definition of, or that's, by definition, that's what the logarithm of 2 minus 2i is. Okay, so let's write this as x plus iy, where x and y are real. And we just computed this to be the natural log of 2 square root of 2 minus I times pi over 4. Okay, so let's multiply out the numerator. The real terms, we have e to the x natural log of 2 square root of 2. And then the two imaginary terms, I times negative I makes plus 1. So we get plus y times pi over 4. Okay, so that's the real parts. Then this gets multiplied by the imaginary part. The x term is going to be negative x times pi over 4. And the y term will be plus y times the natural log of 2 square root of 2. So that is the simplification of this expression. So now that we have this expression, let's start taking these three problems one at a time. So first off, the first problem, number 1, when does this happen? That the modulus is equal to 1. The modulus is equal to 1 when the thing that I'm about to circle here is equal to 1. So when that is equal to 1, then the modulus of the complex number is equal to 1, because this part just provides the directional part. So I need to solve e to the x times natural log of 2 square root of 2 plus y pi over 4 equals 1, where x and y are real. So because x and y are real, this only happens when the exponent, x times natural log of 2 square root of 2 plus y pi over 4 is equal to 0. Or in other words, if we solve for y, we would have that y is equal to negative x times the natural log of 2 square root of 2, and then I multiply by 4 over pi to isolate the y. And so as long as the imaginary part is this constant times x, then 2 to minus 2i to the z will be 1, have a modulus of 1. So that defines in the complex plane a line. So something like this. So there is a line in the complex plane so that every number on this line when I take 2 minus 2i to any number on this line, I get another complex number that has modulus 1. So that's the first part. Second part. For what values of z is 2 minus 2i to the z a positive real number? I get a positive real number. Well, the first part doesn't matter. I get a positive real number when, for the second part, the thing in the parentheses is a multiple of 2 pi. So if the thing in the parentheses, the second set of parentheses from here to here, if the thing in the second set of parentheses is 0, then I would get a positive real number because e to the something would be positive. If this thing in the parentheses is 2 pi, then e to the 2 pi I would also be equal to 1. And so as long as the second set of parentheses is an even multiple of pi, then the result will be a positive real number. So the solution for part 2 is that negative x times pi over 4 plus y times the natural log of 2 square root of 2 has to be equal to some even multiple of pi. And that will force this second term that I'm circling to be equal to plus 1. Okay, so let's get rid of the figure in purple here so I can get some space. And so solving for y, this means that y must be equal to pi over 4 times x plus 2 pi n divided by the natural log of 2 square root of n, or 2 square root of 2. So this doesn't provide just a single line in the complex plane. This provides infinitely many lines in the complex plane where 2 minus 2i to the z is a positive real number. Finally, for part 3, when is 2 minus 2i to the z a pure imaginary number? It is a pure imaginary number when the thing that I'm circling here, this part of the expression, is a half multiple of pi, like e to the I pi over 2, or e to the I 3 pi over 2, or e to the I 5 pi over 2, or e to the negative pi over 2. If it's a half multiple of pi, then the second part here will prove to be either plus I or negative I, which forces the whole expression to be pure imaginary. So for part 3, the answer is that we need that second exponent, negative x pi over 4, plus y natural log 2 square root of 2, to be equal to some half multiple of pi. So n plus 1/2 times pi. And so our answer is going to have kind of the same form as the one we just wrote down for part 2. Y will be equal to pi over 4x plus n plus 1/2 times pi divided by the natural log of 2 square root of 2. And so as long as the real and imaginary parts of the complex number z satisfy this relationship, then 2 minus 2i to the z will be a pure imaginary number. Okay, so this problem was basically an exercise in understanding the definition of taking a complex number and raising it to another complex number.